Beneath the serene surfaces of certain crater lakes in Cameroon lies one of nature's most unusual and deadly hazards. Unlike earthquakes or hurricanes that announce their arrival, these exploding lakes strike silently, releasing invisible clouds of carbon dioxide that can suffocate entire communities without warning. Today, we'll explore the science behind Limnic eruptions, the devastating historical events that brought them to worldwide attention, and the ingenious solutions scientists have developed to prevent future tragedies. On August 21, 1986, residents near Lake Nyos in Cameroon experienced what would become the deadliest Limnic eruption in recorded history. Without warning, the seemingly peaceful crater lake released a massive cloud of carbon dioxide that silently rolled down surrounding valleys at approximately 50 kilometers per hour. This colorless, odorless gas displaced oxygen near ground level, suffocating approximately 1,746 people and thousands of livestock across multiple villages. The deadly cloud affected areas up to 25 kilometers from the lake, giving victims no chance to escape or even understand what was happening. Most people died in their sleep, with no visible injuries, creating scenes that bewildered the first responders who arrived at the site. The few survivors of the Lake Nyos disaster typically had been sleeping in elevated positions where the dense CO2 cloud couldn't reach, or had been away from the affected valleys that night. When international aid workers arrived in the days following, they encountered apocalyptic scenes that resembled the aftermath of a neutron bomb. Buildings remained intact while nearly all living creatures had perished. Entire family compounds were wiped out in an instant. The scale of death necessitated mass graves, as teams worked to address the humanitarian crisis while scientists struggled to understand exactly what had happened. This wasn't the first such event in the region. Lake Nyos had experienced a similar but smaller eruption in 1984, claiming 37 lives. But the Lake Nyos disaster's magnitude forced the scientific community to confront this geological anomaly head-on. These deadly events occur due to a unique combination of geological and hydrological factors. Lakes Nyos and Nyos are situated above volcanic chambers that continuously leak carbon dioxide into the lake bottom. Unlike typical lakes that experience seasonal turnover where deep and surface waters mix, these African crater lakes are thermally stratified, meaning the water forms distinct layers that don't mix. The bottom layers become supersaturated with CO2 under high pressure. At the depths of Lake Nyos, approximately 208 meters, the pressure allows water to hold up to 15 liters of dissolved CO2 per liter of water. When this delicate balance is disturbed by a trigger like a landslide, small earthquake, or even strong winds, it can set off a chain reaction. The gas begins to escape, reducing pressure and causing more gas to rapidly bubble out in a process similar to opening a shaken soda bottle, but on a catastrophic scale. The chemistry behind Limnic eruptions is both fascinating and terrifying. Water can dissolve extraordinary amounts of carbon dioxide under pressure, much more than at normal atmospheric conditions. Scientists estimate that Lake Nyos released approximately 1 cubic kilometer of CO2 during the 1986 eruption. This volume would occupy about 1,000 times that space at atmospheric pressure, explaining the explosive nature of the gas release. The resulting cloud of CO2 is heavier than air, causing it to flow downhill and hug the ground like an invisible flood, displacing breathable air as it travels. Victims of Limnic eruptions typically die from asphyxiation without ever waking up or realizing what's happening. Their bodies show no trauma, only the physiological signs of oxygen deprivation. Blue-tinged skin and blood with the characteristic cherry-red color of carbon dioxide poisoning. Following these tragedies, scientists and engineers developed an innovative solution to prevent future disasters. In 2001, French scientists installed degassing columns in Lake Nyos, pipes extending from the lake surface to the CO2-rich bottom layers. These pipes allow the pressurized water to rise naturally through the column. As it ascends and pressure decreases, the dissolved CO2 forms bubbles that drive a self-sustaining fountain, continuously releasing the dangerous gas in controlled amounts. The fountain at Lake Nyos can reach heights of up to 50 meters, creating a spectacular display of engineering ingenuity. Several additional pipes have since been installed, though experts believe more are needed for complete safety. This degassing solution represents a remarkable example of simple yet effective engineering, as the system operates without external power, using only the natural pressure differential between the lake bottom and surface. The initial installation required priming the pipes with pumps, but the fountains became self-sustaining once started. Monitoring has shown that CO2 levels in Lake Nyos have decreased significantly since installing these pipes, reducing the risk of another catastrophic eruption. Beyond the degassing columns, the engineering team also reinforced the natural dam containing Lake Nyos, addressing concerns about its potential failure, which could have caused devastating floods and gas release. Local authorities have established warning systems and evacuation plans for surrounding communities, while some villages have been permanently relocated from the highest risk areas. These comprehensive mitigation strategies demonstrate how scientific understanding can be translated into practical solutions that save lives, turning a once deadly natural feature into a managed risk. While Lake Nyos and Lake Manoon are the only confirmed examples of deadly limnic eruptions in human history, scientists have identified other lakes with similar potential. Most concerning is Lake Kivu, which straddles the border of Rwanda and the Democratic Republic of Congo. Unlike the relatively small Cameroonian lakes, Lake Kivu is massive, 2,000 times larger than Lake Nyos, and contains not only carbon dioxide but also significant amounts of methane gas. What makes this situation particularly alarming is that approximately 2 million people live along its shores, including the populations of major cities like Goma and Bukavu. A limnic eruption at Lake Kivu would be catastrophic on an unprecedented scale, potentially becoming one of the deadliest natural disasters in human history. Studying these African lakes has expanded our understanding of similar hazards worldwide. Research into limnic eruptions has influenced monitoring systems for volcanic lakes globally and contributed to carbon capture and storage safety protocols. Climate scientists also study these natural carbon dioxide reservoirs to better understand the global carbon cycle and potential impacts of CO2 release from other natural sources. The methane contained in Lake Kivu has also attracted attention as a potential energy resource, with extraction facilities now operating that simultaneously reduce the risk of eruption while providing electricity to local communities. This dual-purpose approach demonstrates how hazard mitigation can sometimes be combined with economic development. Since the Lake Nyos disaster, significant advances have been made in early warning systems for potential limnic eruptions. Automated monitoring stations now continuously measure CO2 concentrations at different depths in these dangerous lakes, transmitting data to scientific centers where any concerning changes can trigger alerts. Local communities have been educated about evacuation routes and warning signals. Some monitoring systems include simple visual indicators that local residents can understand without technical knowledge, colored flags or lights that change based on risk levels. These warning systems represent a crucial layer of protection beyond the physical degassing solutions, especially important as the degassing process for lakes like Nyos is ongoing and not yet complete. The combination of continuous monitoring and public education has transformed how these communities live with risk. The limnic eruptions in Cameroon didn't just take lives, they transformed entire communities and cultures. In the aftermath of the Lake Nyos disaster, survivors faced not only grief but displacement, as many were relocated to new settlements away from the danger zone. Traditional connections to ancestral lands were severed, and cultural practices tied to specific locations were disrupted. Some communities developed new folklore and spiritual beliefs around the lakes, viewing them as places where ancestral spirits had expressed displeasure. The disaster also created a generation of orphans and fragmented family structures. International aid efforts helped rebuild physical infrastructure, but the social and cultural rebuilding has been a longer process. Today, some communities hold annual remembrance ceremonies for those lost in 1986, keeping their memory alive while embracing the scientific understanding that now helps protect them. The response to Cameroon's exploding lakes represents a remarkable example of international scientific cooperation. After the Lake Nyos disaster, researchers from Africa, Europe, North America, and Asia collaborated to understand the phenomenon and develop solutions. This collaboration transcended geopolitical boundaries, with scientists from countries that might otherwise have limited interactions working side by side in the field. The degassing technology itself was developed through multinational efforts, with components manufactured in different countries before being assembled in Cameroon. Funding for both research and mitigation came from international sources, demonstrating global solidarity in the face of an unusual natural hazard. This model of scientific diplomacy continues today, with international teams still monitoring these lakes and sharing data openly with the global scientific community. As our planet warms, scientists are considering how climate change might affect the stability of lakes prone to limnic eruptions. Rising temperatures could potentially alter the thermal stratification of these lakes, affecting how gases accumulate and potentially increasing risk. Changes in precipitation patterns might also impact lake levels and the stability of natural dams containing these bodies of water. While there's no evidence yet that climate change has directly increased the likelihood of limnic eruptions, researchers maintain vigilant monitoring for any shifts in established patterns. The knowledge gained from studying Cameroon's lakes may become increasingly relevant as we face a future where many natural systems are being pushed into new states by human-induced climate change. The engineering solutions developed for these African lakes might also inform adaptation strategies for other climate-related hazards. Looking ahead, the management of dangerous lakes like Nyos, Manoon, and Kivu will require ongoing commitment and evolving strategies. The current degassing systems require maintenance and eventual replacement. For Lake Kivu, the dual approach of hazard reduction and methane harvesting for energy continues to develop, with new extraction platforms being installed. Scientists are also exploring more advanced monitoring technologies, including automated underwater vehicles that can map gas concentrations in 3 dimensions. Some researchers propose more permanent solutions, such as artificially inducing regular mixing in these lakes to prevent gas buildup in the first place, though such approaches would require careful testing to avoid triggering the very events they aim to prevent. What's clear is that these lakes will require human management indefinitely. They represent natural hazards that, once understood, cannot be left unattended. The story of Cameroon's exploding lakes represents both one of nature's most unusual hazards and humanity's capacity to understand and mitigate such dangers. From the tragedy of nearly 1,800 lives lost at Lake Nyos emerged valuable scientific knowledge and innovative engineering solutions that have likely prevented further catastrophes. The degassing columns, simple in concept yet profound in impact, demonstrate how understanding natural processes can lead to effective interventions. As we face a future of climate uncertainty and growing populations around geological hazards worldwide, the lessons from these African lakes take on added significance. The international cooperation that followed these disasters shows how shared scientific challenges can transcend boundaries and bring diverse expertise to bear on problems that no single nation could solve alone. While the threat beneath these placid waters remains, the combination of scientific monitoring, engineering solutions, and community preparedness has transformed deadly lakes into managed risks, a testament to human resilience and ingenuity in the face of nature's most extraordinary phenomena. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.